On July 20th, 1969, two astronauts hurtled towards the moon when suddenly alarms started blaring throughout their spacecraft. The computer, their only way to land safely, was failing. But that moment wasn't just about the astronauts, or even the rockets. It was about 145,000 lines of code that had to work perfectly the first time. Because in space, you don't get second chances.
It's one small step for man, one giant leap for mankind.
As a principal software engineer, I'm going to show you how this code changed more than just the course of the mission. It revolutionized computing as we know it. To understand why this code was so crucial, let's look at what the Apollo 11 needed to accomplish. The mission launched 4 days earlier on July 16, 1969, carrying 3 astronauts, Commander Neil Armstrong, Commander Module Pilot Michael Collins, and Lunar Module Pilot Buzz Aldrin. But most people didn't know this spacecraft actually consisted of 3 major parts: the Saturn V rocket for launch, the command module Columbia for the journey, and the lunar module Eagle for landing. And each part had its own critical ring, but 2 of them, Columbia and Eagle, needed their own navigation and guidance system. Now this is where the Apollo Guidance Computer, or AGC, comes in. The AGC was a revolutionary piece of hardware for its time. Each spacecraft had to have one, and identical in build, but running different software for their specific tasks. Apart from the 2 to 4 kilobyte, depending on who you ask, of erasable RAM, programs themselves had to be stored in only 36 kilobytes of read-only memory. Also, since these components would be enduring harsh accelerations and forces on the rocket, they needed to develop memory that wouldn't fail at any cost. The solution was the core rope memory. This was literally ones and zeros weaved into a board on a loom by textile workers. This gives a whole new meaning to storing strings. The processor ran on integrated circuits, and this was the first time that ICs would be used in a computer. In fact, this technology was so new, the production engineers didn't even know how to test them. Now here's where it gets wild. This computer wasn't just running one app at a time. It was juggling all the mission-critical stuff simultaneously, like the navigation map that was constantly recalculating their position in space, the thruster ballot, which precisely fired engines to stay on course, a life support systems, this was to make sure that they didn't suffocate or freeze, and an error detection program. This catch problems before they became disasters. But the 400-person team led by Margaret Hamilton didn't just write code. They invented modern software engineering practices that we still use today. This code was written in a special interpreted assembly language, meaning that every instruction had to be meticulously crafted at the lowest level. One character could mean disaster. What made this code truly revolutionary was its ability to handle errors, and the story behind this innovation starts with a child's curiosity. One day, Hamilton brought her young daughter Lauren to the lab at MIT. Lauren, playing astronaut, started pressing buttons on the module simulator, but not in the expected order. She pressed the DSKY keys during a pre-launch program P01 while in the middle of a flight, something an astronaut would normally never do. Now, this caused the system to completely crash. Hamilton watched as her daughter accidentally revealed a huge critical flaw. There was no protection against human error. If her daughter could crash the system, an astronaut under pressure certainly could too. Now, this led to Hamilton's team to completely rethink how computers should handle errors. Think of it like a juggler with multiple balls in the air. Now, a normal computer at that time was like a juggler who just dropped all the balls when they make one mistake. But Hamilton's team created something different. They built a system that could be like a skilled juggler. Keep the most important balls in the air, even if they had to drop a few less critical ones. This became what we now call priority scheduling. The computer would constantly ask itself, what is the most critical task right now? And what can I temporarily ignore if I'm overwhelmed? They programmed different priority levels for every task. Highest priority, of course, navigation and life support. Medium priority, system monitoring. And the lower priority, just their routine calculations. The system could instantly reshuffle these priorities if something went wrong. It was revolutionary. Computers before this would simply just fail if they got overwhelmed. This wasn't just clever programming, it was a fundamental shift in how we think about software. Hamilton and her team realized that writing code isn't just about telling a computer what to do when everything goes right. It's about preparing for when everything could go wrong. Today, every computer you own uses these same principles. When your phone is running low on memory, it doesn't just crash, it starts closing background apps to keep the most important ones running. That is a direct legacy of Hamilton's innovation, all because her daughter decided to play astronaut one day. This innovation, priority-based scheduling, faced its ultimate test on July 20th, 1969, during the Apollo 11 lunar landing. As the lunar module Eagle descended towards the moon's surface, alarms began blaring in the cockpit. These were 1202 and 1201 program alarms, cryptic warnings indicating that AGC was overloaded with tasks. The issue stemmed from a rendezvous radar, which was left on standby during the descent as a precautionary in case an abort was needed to dock back with the command module. Due to a wiring issue, the radar sent a constant stream of irrelevant data to the AGC, consuming critical processing power. To make matters worse, Buzz Aldrin entered a command 1668 to display the altitude differences, further increasing the computer's workload by 10%. At this point, the AGC was operating at nearly 95% capacity. This was an incredible, precarious situation for such a critical phase in the mission. Without its innovative priority system, this overload could have caused the computer to crash entirely, forcing an abort and jeopardizing the mission. Now instead, the AGC did exactly what it was designed to do. It identified and prioritized essential tasks like navigation and engine control while temporarily ignoring the less critical ones, such as processing radar data or displaying non-essential information. Despite being overloaded, the computer maintained control of critical systems, ensuring a safe landing with just 20 seconds of fuel remaining. At 4:17 Eastern Standard Time, Armstrong radioed back to Earth.
Tranquility Base here. The Eagle has landed.
Humanity had achieved its first successful moon landing. The concepts developed for Apollo 11's code revolutionized computing. We had multitask operating systems, real-time error handling, priority-based scheduling, and human-computer interfaces. These same principles are used today in everything from smartphones to laptops. The original Apollo 11 code was released on GitHub in 2016. It's amazing to see this historic code even containing some witty comments. You can take a look for yourself, linked down in the description below. The next time you hear about the Apollo 11, remember, it wasn't just about the astronauts and the rockets that got us to the moon. It was 145,000 lines of meticulously crafted code, written by pioneers who had just invented the future of computing just to make it possible. If you're interested in more stories about technology that shaped history, check out this history on JavaScript here. Otherwise, I'll see you in the next one.